Congratulations, you made it to the end of this very overwhelming meeting. Now you can go home and sleep. But first, we have some more exciting news coming out of the press room for you. So today's press conference, this is Thursday. It's 2:15 p.m. in Louisiana. And this is Thursday, the 11th of January. And we are now entering the press conference Oddities in the Sky. My name is Susanna Kohler. I'm the press officer for the AAS, and I am assisted today by Deputy Press Officer Carrie Hensley and AAS Media Fellow Benjamin Casses. They will be running mics and taking questions from reporters who are watching online. So before we get started, just a quick reminder to silence your cell phones or anything else that might make noise and interrupt the proceedings. And just for anyone who hasn't been to a press conference here before, the way this is going to work is that I'm going to give a brief introduction to the topic and to our panelists. Then they are going to go through and present in order. And then at the end of that, we will move into a joint Q&A session for all of our speakers. So hold all of your questions until that point. And then we'll take questions from anybody in the room and anybody online who has them. And when we do move into the question session, if you could please, if the microphone comes to you, identify yourself and your affiliation and who your question is for before you ask the question. Just a quick update on previous press conferences. We've got most of the videos for the briefings, as well as the press releases associated with them and the slides going into the press kit. The press kit is online on the meeting website in the press information section, and you can also get to it from the press conference's Slack. It is pinned in that channel. So, moving forward. As I said, we are going to be talking about oddities in the sky in this session. This is a bit of a hodgepodge session of cool things that you can see when looking out. We're going to start out today with A Big Ring on the Sky by Alexia Lopez from the Jeremiah Horrocks Institute and University of Central Lancashire. Then we're going to hear about a potentially isolated quiescent dwarf galaxy from Timothy Carleton of Arizona State University. Next, we're going to hear about close encounters of the supermassive black hole kind, tidal disruption events, and what they can reveal about black holes and stars in distant galaxies from Ananya Bandopadhyay, and she's from Syracuse University. And lastly, we're going to hear about Zuniverse people-powered research platform and how it has reached new milestones from Trouille of the Adler Planetarium and Zuniverse. So with that, I am going to get us set up over here. And I will turn it over to Alexia.
Hi everyone, my name is Alexia Lopez. I am a PhD student at the University of Central Lancashire in the UK under the supervision of Dr. Roger Clowes and Dr. Jerry Villiger. Today I will present A Big Ring on the Sky, which is my second large-scale structure discovery that further challenges our understanding of the universe. This is an overview of my talk, and I will start with a quick intro into the background. The standard model of cosmology, the lambda cold dark matter model, is the most successful model to describe our universe and everything in it. The mathematics to describe our universe relies on an assumption that on large scales, the universe is both homogeneous, the same everywhere, and isotropic in all directions. This is known as the cosmological principle. Since the standard model is built upwards from this assumption, it's imperative that we prove that the universe really is homogeneous and isotropic. To test just the homogeneity, we can look at the large-scale structure of the universe, since the assumption essentially puts a theoretical limit on the size that structures can exist. This is known as the scale of homogeneity, and it's estimated to be about 1.2 billion light years. So structures exceeding these scales present a potential challenge to our cosmological principle. Previously, in 2021, I presented my first large-scale structure discovery, a giant arc on the sky, at the 238th AAS conference. This is a large-scale structure of galaxies and galaxy clusters extending 3.3 billion light years, almost 3 times the scale of homogeneity. is located 9.2 billion light years away, so when the universe was only half its present age. This structure added to an accumulating set of large-scale structures, posing challenges to our cosmological principle. The method of my work here is the same that I used with my giant arc discovery. I make use of the very bright, very distant point sources of light known as quasars, represented by the yellow star shapes. In a side-on view, we can see that as the quasar light travels across the universe, it can pass through clouds of matter around galaxies and galaxy clusters. This then leaves a distinct feature in the measured light from the quasar. In the face-on view, we can see that the quasars act like spotlights in a dark room, highlighting to us where this intervening matter is. We can see there are many more quasars than matter clouds, but where there isn't a quasar, we cannot detect that galaxy or galaxy cluster. So this is represented by the black cloud. So we need the quasars in order to see these distant, faint galaxies. So we have the position of the galaxy, which is the position of the quasar. They're the same. We can measure the distance to the galaxy from the distinct feature in the measured quasar light. So what we're actually measuring is the wavelength of the magnesium-2 absorption doublet in the spectra of quasars. So this is seen in the figure to the right. You can see the distinct feature labeled with 2 parallel lines. So these are our magnesium-2 absorbers. So we have position, we have distance. So we have a 3D map of the faint distant galaxies. And we can use this to map our large-scale structure of the universe. My newest discovery is a big ring on the sky. It's a large circular structure of magnesium-2 absorbers spanning a diameter of 1.3 billion light years and so a circumference of 4.1 billion light years. This is even bigger than my previously discovered giant arc. It's also 9.2 billion light years away, which is the exact same distance as my previously discovered giant arc. In fact, if we could see both structures on the sky, they would only be separated by 12 degrees. So cosmologically, these structures are really close together, which is really interesting. We did some statistics and find that the big ring has a significance of 5.2 sigma. So this is exceeding that 5 sigma golden threshold. So together and independently, these structures challenge our cosmological principle by adding to this accumulating set of large-scale structures exceeding the scale of homogeneity. So what does it mean? We have these pressing questions. Can the universe really be homogeneous if we're finding more and more of these large-scale structures exceeding the scale of homogeneity? Is the cosmological principle at doubt? And if so, will our standard model hold? Perhaps it's time to turn to new avenues, such as alternative theories in cosmology. Cosmic strings were once thought to be able to explain large-scale structures, and recently they've begun appearing in papers, including one from Nobel Prize winner Jim Peebles. Conformal cyclic cosmology is an alternative theory in cosmology proposed by Nobel Prize winner Roger Penrose. This suggests that we live in a single eon of time, in a possibly infinite cycle of universes. And if so, we would detect circular features in our CMB sky. Today, I have presented my second ultra-large scale structure found with the magnesium-2 method. It's a big ring on the sky spanning 4.1 billion light years in circumference. It adds to an accumulating set of large-scale structures exceeding the scale of homogeneity, and so it adds another challenge to our cosmological principle, It leads to the ultimate question: do we need a new standard model? Thank you so much.
All right. Hello, everyone. My name is Timothy Carleton, and I'm an assistant research scientist at Arizona State University. And today I want to tell you about a galaxy that showed up unexpectedly, but turned out to be really, really interesting and kind of challenge our idea of how galaxies can form and evolve. And this is a galaxy I'm really excited about. So the story starts with this image of the galaxy cluster CLG 1212, taken with the James Webb Space Telescope early last year as part of the PEARLS program. And as you're looking at this image, I'm sure you've seen a lot of images like this over the past week or year or so. It's really amazing what this new telescope can do. Look at all the individual galaxies and all the different galaxy shapes and sizes and colors. I want you to think about the galaxy that for you could have the biggest impact on our understanding of galaxy evolution. For me, it's this galaxy right here. If you weren't too impressed by this galaxy at first, that's okay, because neither was I. When I first saw this image, I thought it was kind of neat that we had an additional galaxy in this imaging that we weren't expecting, but I didn't think it would really be that interesting or really have a lot to teach us. But as I looked at this galaxy in more and more detail, I came to find that its properties were really unexpected, and it really can teach us a lot about how galaxies form. And so we have the three main interesting aspects of this galaxy are first, that it's unexpected. We were mainly interested in the galaxy cluster off to the right, that we're looking at the galaxy cluster properties and all the galaxies behind it that are magnified through the effect of gravitational lensing, because we weren't expecting to see any other galaxy over here. The fact that we saw it was really unexpected and I think pretty interesting. But furthermore, this galaxy shows up in an impressive amount of detail. This is possible with a high resolution and high sensitivity of the James Webb Space Telescope, that we're really able to identify the individual parts of this galaxy really well. When we look at the properties of this galaxy, it turns out to be really unexpected and challenging our theories for how galaxies form and evolve. And so I'll touch a little bit on these last 2 points about how detailed and interesting this galaxy is. So first of all, I'll zoom in on this image of this galaxy PEARLS, which I'm calling PEARLS DG. And you can see in that image all these individual dots of light that you see. These are all stars that we're seeing in this galaxy 100 million light years away. And for context, the nearest massive galaxy, Andromeda, is a few million light years away. So the fact that we're seeing all these detailed stars out to much further distances than we've been able to before is really impressive and shows the promise of this great new telescope. And while we've seen stars beyond the Milky Way with JWST before, this is really the furthest that we've been able to resolve all these individual stars in quite this level of detail with JWST. That's important because we want to understand the properties of this galaxy really well, because it turns out to be pretty unexpected. We really want to understand kind of have the best understanding of what's going on. So to explain kind of why this galaxy is unexpected, I'll show here a few examples of similar galaxies to PEARLS DG. They have similar masses. We would expect them to have similar formation histories. Well, you notice that you have 2 really blue galaxies and 1 red galaxy here. The two blue galaxies, these are composed primarily of lots of young stars, a lot of ongoing star formation. We have this red galaxy here also, and this is not having as much ongoing star formation, a little bit older stellar population, but it's interacting with this nearby massive galaxy. And as you expand your search to thousands of more nearby galaxies, this picture generally holds. You either have an isolated galaxy that's continuing to form stars, has a lot of young stars, or if you don't have this young star population, you're interacting with a more massive galaxy. And because we were seeing this in all of our observations, we really built up this theory for galaxy evolution that didn't really have a canonical way of having a galaxy that's by itself, but not forming any stars. But then we observed this PEARLS DG galaxy. This is a galaxy that's really pretty far away from any group or massive galaxies, and it really has a pretty old stellar population. It's not really forming any new stars. And I'll acknowledge that this is the first time we've observed an isolated quiescent galaxy like this, but this, I would say, is a particularly extreme example where it is pretty far away from any massive structure, and it really has a pretty low star formation rate. And also, we're able to see it in an impressive amount of detail, allowing us to really understand its properties. And the fact that we're just seeing this galaxy by happenstance after just 1 year of JWST imaging suggests that we're really looking at a population of galaxies that's a significant population of galaxies. And it's something we really need to be able to fit into our understanding of how galaxies form and evolve. And I don't have a particular example of thought of how this galaxy could form, but I know we're already starting to think of a lot of different ways we could have this, and I'm excited to think about this more and fit this into our theory of galaxy evolution. So I'll put up my summary here. This Pearls DG galaxy showed up unexpectedly in JWST imaging, and is something we're able to see in really exquisite detail, identifying all these hundreds of individual stars in the galaxy. And this galaxy is challenging our theory for how dwarf galaxies form and evolve. It's pointing to a new mechanism for forming these dwarf galaxies. I'll note that this paper has been accepted for publication in Astrophysical Journal Letters, and you can see it on this archive link here. Thank you.
So, hi everyone, I'm Ananya Bandopadhyay and I'm a graduate student at Syracuse University. I'll be talking about tidal disruption events and what these can reveal about black holes and stars in distant galaxies. This is work that I've done with my advisor, Eric Coughlin, who's here today, our collaborator, Chris Nixon, who's at the University of Leeds, and graduate and undergraduate students in our group, two of whom, Julia and Dan, are also here today. Also, 4 of our co-authors are high school students from the Syracuse City School District who worked alongside us during a summer research program that I'll talk more about in a little bit. This work was published today in the Astrophysical Journal Letters, and you can access that using the QR code that I've put up here. So to set the stage for what I'm going to be talking about, I have an animation of a tidal disruption event. So this is a star, something like our sun. And this interacts with a supermassive black hole, which is an object that has the mass of about 1 million of these suns condensed into a very small region of space. So the gravitational field of these supermassive black holes is so strong that not even light can escape from them, which basically means that these objects are dark and they're very hard to observe. But when we have a star coming in close proximity to a, sorry, that's supposed to be a video. I don't know why the video is not playing. Sorry. Okay. Okay, so when a star comes in close proximity to the supermassive black hole in certain scenarios, it can be ripped apart by the tidal forces of the supermassive black hole. And then the shredded stellar debris will over time accrete onto the black hole and generate a luminous flare, which we can observe as the tidal disruption event. So because of the immense potential that these tidal disruption events have for illuminating supermassive black holes at the centers of galaxies, their light curves have been modeled as a theoretical pursuit long before TDs were actually observed. But now about 100 of these events have been observed at multiple wavelengths. And the figure on the left is showing you a set of TD light curves from the Zwicky Transient Facility. I've taken this from the Hammerstein et al. Paper. And you'll see that for all of these light curves, they rise on a timescale of something like 30 to 50 days, reach their peak, and then subsequently fall off. So I've singled out one of these on the right-hand side figure to show that there's a characteristic timescale associated with the peak luminosity of all of these light curves, which is about 30 to 50 days. And the question that we are trying to address in this paper is what determines the peak luminosity in a tidal disruption event light curve, and also the characteristic peak timescale that's associated with this. So to determine the peak luminosity, what we can do is numerically simulate this tidal disruption event for a bunch of stars and determine the fallback rate of stellar debris, because the fallback rate is the determining factor for luminosity in a TDE. And however, these simulations often tend to be computationally expensive. So people have often come up with semi-analytic models, which make some assumptions about the ongoing physics, but try to estimate the same observable properties. So what I'm showing you on the left-hand side is a fallback rate in solar masses per year as a function of time in years. And the solid pink curve that you see is showing the disruption of a 3 solar mass by 1 million solar mass black hole. And this is from the hydro simulation of a TDE. So this is supposed to be accurate. And the dashed curve that you see here is from the frozen in approximation, which is a tidal disruption event model that has existed since people have been studying TDEs. This is one of the earliest TDE models and also widely accepted in the TDE community. So as you can see, what should ideally have been the same curve, or at least very close to one another, seems to be disparate from one another. And at the peak, the frozen in approximation type is different from the prediction of the simulation by 2 orders of magnitude, both in peak luminosity as well as on the peak time scale. So obviously there's something missing in the frozen in approximation. And to illustrate this further, on the right, I've shown a plot of these peak luminosities as a function of the peak time scale for a bunch of stars that we evolved with the stellar evolution code MESA. And the color on the legend shows you the mass of the star, whereas the marker style shows you the age. So what this is demonstrating is these 3 lines, sort of horizontal-ish lines that you see at the bottom, are the predictions of the frozen in approximation. And this tells us that as you increase the mass of the star, the timescale associated with the peak luminosity increases to more than 1 to 10 years for the high mass stars in the mass range, like 2 to 5 solar mass. And the peak luminosity, the magnitude of the peak itself, goes down a little bit and then increases beyond a certain point. But the point here is that this prediction is very discrepant with the numerical simulations. So can we do better than the frozen in approximation? So to answer that question, I'm going to direct you to a new analytics model that Eric and his collaborator Chris came up with in 2022. And that's the citation that you see here. You can refer to the details of the model in this paper, but I'm going to be highlighting the predictions of this. So we used the CN22 model to predict the same things, the peak luminosity and peak timescale associated with the disruption of this range of stars. And the predictions of this model are basically the cluster of points that you see at the top here. And it's a little hard to see in the year timescale. So I've zoomed in on this and showed the timescale in days. So it's this cluster of points. And this model says that irrespective of stellar properties like mass and age, you get a peak timescale of about 15 to 35 days for all of these stars. And the magnitude of peak luminosity scales approximately linearly with the mass of the star. So this actually turns out to be in very good agreement with numerical simulations that we have compared it against, leading us to believe that this has immense potential in terms of observations of TDs in the future. But the summary of this model is that you obtain a peak timescale of 30 days, which is quite independent of stellar properties and is primarily determined by the mass of the supermassive black hole, thus allowing us to directly probe properties of supermassive black hole, which are otherwise so hard to observe. So this model has other important observational implications, which we have outlined in the paper, but in the interest of time, I'll limit it to the discussion of one particularly interesting implication. So jetted TDEs, which are associated with the launching of relativistic jets from TDEs. So we believe the driving mechanism for launching such relativistic jets is something like very high super Eddington accretion rates. And the CN22 model tells us that such high accretion rates can be obtained from the disruption of high mass stars, as you can again see in the figure here. So these jetted TDEs have rarely been observed, and this model suggests that a possible explanation for the rarity of these jetted TDEs is the intrinsic rarity of high mass stars in our universe. And also, if you were to follow up the host galaxies of these TDEs, you'd be likely to observe that these come from young star-forming galaxies, because high mass stars have a short lifetime, so these galaxies would still likely to have these stars around. So there are other important observational implications that we have highlighted in the paper. You can access the paper, but I'll end with the Syracuse University Research and Physics program again. So this is a program that our department has been organizing since the last 2 years. And we bring in about 10 students every year in a cohort who work with different faculty in the department over a period of 6 weeks. So we in the Astro group have worked with 4 of these students over the last 2 years. They worked alongside us to test the CN22 model and are all co-authors in the study. You can see the poster session from this year out here. So I think this is a great way of engaging high school students in research and giving back to the local community in Syracuse. So I put up my contact info up here and also Eric's contact info. Feel free to reach out if you have questions, and thank you.
Hi, everyone. I'm Laura Trouille, PI for Zooniverse and VP of Science Engagement at the Adler Planetarium in Chicago. It's been a fantastic AAS. I hope you've enjoyed it as much as I have. There's so many great talks, conversations, and especially so many bright new minds that are entering our field. It's very energizing. A critical component of a healthy research community are the robust tools and shared infrastructure that we have available to us. And so this little preface brief is all about celebrating Zooniverse, one of our shared pieces of infrastructure that has led to breakthrough discoveries in astronomy and beyond. Zooniverse is the world's largest platform for people-powered research, also known as citizen science. The open source platform powers research across the disciplines, from tagging penguins to transcribing historical documents, to discovering planets around distant stars, to marking cells for cancer research, and more. This year, we welcomed our 2.6 millionth registered participant and have had a tremendous output of over 100,000 classifications coming into our projects every day. So Zooniverse began in 2007 with a single project, engaging the public in classifying galaxies through the Galaxy Zoo project. Since then, we've launched over 400 projects. A game changer was the launch of our DIY project builder in 2015. It enables anyone to build their own crowdsourced research project through Zooniverse for free with simple browser-based tools. We went from building 3 to 5 custom projects each year to supporting the launch of 40 to 50 new projects annually. Each project is led by a different research team, and we partner with an incredibly diverse range of institutions: universities, national labs, museums, libraries, government agencies, and more. This shared infrastructure, with its sophisticated API, ability to scale quickly, machine learning fully integrated into it, and accessible design, coupled with a tremendous participation from the public, has been transformative for research. Zooniverse is a core part of our research infrastructure landscape. It's changed the types of questions that researchers can ask, and it's a critical tool in our ability to fully take advantage of the large data sets that are characteristic of modern science. To date, there have been over 400 peer-reviewed publications that have come from Zooniverse projects. As an example, just 2 days ago, Nora Eisner and her team's latest Planet Hunters test project article was accepted. So this is sifting through hundreds of thousands of light curves. Planet Hunters test is particularly good at finding the unusual. So our latest discovery is of a planet with a 270-day period in the habitable zone of a sun-like star that also has a companion star. So discovering long period planets is relatively rare, let alone in multi-star systems. Without Zooniverse participants' eyes on these data, we would have missed this fascinating discovery. And what I love is that the tens of thousands of participants not only classify the light curves and are acknowledged in the paper, but a good number get involved in a deeper analysis and are co-authors on the publication. As another example, just to give a sense for the breadth within astronomy discoveries on Zooniverse, also just this week, the Backyard Worlds team announced the discovery of Aurora in an extremely cold brown dwarf. So we see Aurora on Jupiter and Saturn, but what's wild here is that there's no obvious external heat source or companion. So Jackie Faraday and the Backyard Worlds team have had tremendous scientific output over the years, with over 30 publications to date, often with participants as co-authors. And I'm thrilled that Dan Castledon, one of the Zooniverse participants in this project and others, was awarded the AAS Chambliss Amateur Achievement Award today. It's congrats to Dan and the whole Backyard Worlds team. So all of this is made possible because of the Zooniverse participants. In the previous year, people collectively spent 1.6 million hours working on Zooniverse projects. That's 182 years of worth of effort just in this past year. It's an amazing contribution. Another way of thinking about it is to convert this time into full-time equivalents or FTEs. So one person working 40 hours per week for 2,000 hours a year, that's one FTE. So our 1.6 million hours is equivalent to 780 FTEs. It's as if we had a building with 780 people who only came in every day, all day to click on Zooniverse projects. And what's wonderful is that our 780 metaphorical people and the 182 years they represent are not confined to one building or one crazed person. Our community is made of millions of individuals across the entire world, 2.6 million registered participants and many more. Some of them have contributed a single classification. Others have given our researchers far, far more of their time and attention through clicking on our sites, discussing ideas on the talk discussion forums, or just spreading the word. So Zooniverse volunteers are making significant contributions to research in areas from astronomy to zoology, cancer research to climate science, arts, and humanities. So it's one thing to celebrate, but especially for those joining online, I very much welcome you to participate. So earlier this week, we launched our latest Zooniverse NASA project, the Burst Chasers project. In this project, we need your help to decode the most powerful explosions in the universe. Amy Lean's talk as part of this AAS press series on Tuesday was a great overview of the science. So we need your help. We need your help to figure out what's causing these weird gamma ray bursts. Is it supernova, black hole mergers, or something more exotic? And as part of this press brief, I knew I wanted to highlight a second project. With over 20 astronomy projects to choose from, it was like choosing your favorite child. So I apologize to all the other children. But as another example, to give a sense for the range, again, across astronomy, is the Daily Minor Planet. So this is another active astronomy project on Zooniverse. It's hunting for asteroids in the Catalina Sky Survey. So it's wonderful if you want to just pop right over to that project and give it a try. So thank you to our volunteers, to our researchers who help create the supportive, inclusive STEM community online, and to our funders. Please don't hesitate to email me with any questions or if you'd like to collaborate on the research side or on the outreach, the education side together. Thanks.
Wonderful. Thank you so much to all of you. So let's see. Okay, we're going to go ahead and move into our Q&A session now. So sure.
Hello, it's Chris Lintop from BBC Sky at Night. I've got a question for the first speaker about the giant ring. It's intriguing that those two structures that you found are at the same distance, you said. Does that mean can you rule out that there would be structures, say, this side of that distance? In other words, is that a particular distance where you seem to find those things and there aren't any others? Or is it a coincidence that the first two that you found are at the same distance?
Thank you for your question. Yeah, so at the moment, both structures were found accidentally. So, which is great. I do have a full catalogue of these magnesium-2 absorbers. And I did actually start creating an algorithm for going through the whole database and then using my statistical methods to then output all of these structures. And, I actually did this in 2021. I went to Chile, and then when I got back, my laptop broke, which was awful. So then that got sidetracked. But the point is, and I still have time to look through all of these absorbers to see if there are other structures. But in terms of the big ring and the giant arc, it is particularly interesting and special that they are next to each other. But until I can look through the rest of the data, I won't know whether this is the only case or whether there are more things out there like this. Thank you.
Grover Chilling, freelance writer from the Netherlands, also for Alexia. You see a ring on the sky. Can we be sure that it's just a ring, or do you expect it to be a sphere? And if so, would you be able to see the galaxies on the front and the back end of the sphere? I realize the density would be lower, but maybe you can trace out a whole sphere, if it's a sphere.
Thank you for your question. So I have done some more 3D analysis of the Big Ring, and actually what I didn't mention, but I did show on my last slide, is different viewing angles of the 3D distribution of the Big Ring. So what I found is that the Big Ring looks a little bit more like a coil. It looks a little bit more like a coil, like a corkscrew face on, so that if you were looking at it, you'd see the circle shape, but if you were to look at the side, you'd realize it was a little bit more coily. We find that the majority of the absorbers are contained within the central part of that Big Ring in a really thin, flat section. So it seems to be that the full ring could be mostly contained within the middle section of this Big Ring, but there is like a curve going into this and a little bit of a broken curve coming out, which makes me think it's more of a coil type shape. But a sphere would also be really interesting if it was. I did look at other redshift slices, so other slices of sky that were a little bit more further out, and this was actually more of a test to make sure that there wasn't some kind of like thing in the quasars, like making this up accidentally. So I did check other redshift slices to make sure this wasn't a problem of the quasars. So you don't see more of this as you look closer towards us. So it does seem to just be contained within that slice of sky. If that answers your question.
Leslie Sage from Nature, for Alexia. At some level, we know that the cosmological principle doesn't hold because we have the cosmic web. And those structures are growing at even redshift of 30. So why are these just not random fluctuations in the cosmic web?
Yeah, so that's a really good question. So obviously, the closer we look, as in the smaller scales we look at, the more likely we are to see structuring, like in the cosmic web. This is normal, and we expect this. The reason why, so the Big Ring is particularly interesting, and structures like the Big Ring, the giant arc, and other huge large-scale structure discoveries like huge large quasar groups in quasars, or giant gamma ray burst ring and gamma ray burst. So what we're finding is this accumulating set of really, really big structures, and we want to find at some scale there's going to be statistical homogeneity. So yes, we can expect random flukes in the statistics from, in the large scale structure, we can expect some occasional flukes. But we're now finding this, as I say, this accumulating set of really, really big structures. In addition to that, we can be a little bit more certain about whether or not it's just a fluke if we use other independent data. So I have also used independent data, not just the magnesium-2 absorbers, but also quasars in that field of the magnesium-2 absorbers. And I applied a statistical package on both the magnesium-2 absorbers and the quasars, and the filament that it detected was actually very, very similar. So we can have independent corroborative data, and also about it being a fluke, it's not just the Big Ring anymore. So what makes it even more interesting and maybe even more confirmation of its reality is the fact that it's so close to the giant arc as well. So to have it just be a fluke is one thing, but to have both things to just be a fluke is even more, difficult. So does that answer your question?
No.
Okay.
So what I'm really getting at is that, when you stand back and you look at the whole universe, the cosmological principle largely holds. But, when you've got the cosmic web, you've got filaments all over the place. And these filaments grow according to gravity
Yeah.
with time, and then, but some filament, why don't some filaments just look like arcs or circles or corkscrews? So
Yeah, so they can, and they can, and you've got to kind of take each large scale structure and assess it individually. So, you know, the giant arc, the big ring, they're both at a redshift when the universe was only half its present age. So, you know, like in our nearby universe, we can expect to see a lot of these filaments actually, because they've had so much time to develop into these, because, you know, filaments and circles and arcs and things like this. So we're not just, you know, it's, yes, we have the cosmic web, and yes, this is okay. And statistically, this is also okay. So when we're looking at large scale structures and we're trying to assess their meaning, we have to apply the statistics of what we would expect to find, for example, at that redshift, so at that time, and whether or not, you know, it's posing this challenge to the homogeneity. The further back well, not the further back we look, but on the larger scale that we look at, we should start to gradually find that even though when you look a little bit closer, you find all these webs and filaments, when you step back, you should start to see that this is statistical homogeneity. So it should represent that of a random point distribution. And so this is why we have this scale of homogeneity. And it's not a cut-off limit, absolutely any structure that's bigger than this is awful and it destroys our cosmology and our models or anything like that. But it definitely starts to raise the question of, you know, how did these structures form? Is it statistically homogeneous on these scales, and how big do we have to go in order to get statistical homogeneity, and our matter distribution representing that of a random point distribution?
Go to Ethan next.
Hi, this is Ethan Siegel from Starts with a Bang. Hi, Alexia. Surprise. I've noticed a lot of these claims over the years that I've been in the field. The closed Campuso LQG, the huge LQG, the giant arc, the big ring, that all come from the same group, the same people, and the same university now which you're a part of. The community has been very skeptical that these structures are actually structures. What I'm hearing from you is a lot of confidence that this is real, that it's really this big, that it's really a gravitationally bound single structure, that it's really a large-scale feature of the universe. How have you tried to knock down this fantastical interpretation? How have you tried to measure the mass and the mass distribution of this structure? How have you attempted to determine if it's gravitationally bound rather than just a visual association of things that are unremarkable that happen to be in the same place? And what would you say if one was inclined to be skeptical? Is the minimum viable scenario now for the null hypothesis that these are not physically real superstructures in order to hold?
Okay, yeah, so that's a lot to unpack. So you raise a very good point. And obviously, you know, in the scientific community, this is how we do good science. We push back, we argue against these being, you know, how statistically real these things actually are and where our confidence can be. So my personal confidence is just, this is fun, but it's not that I don't also have skepticism about the reality of such large scale structures, just like everybody else. So one of the exciting things, but also very difficult things about large scale structures in the universe is that they aren't gravitationally bound. So we have to use statistics to assess these things. So the clouds Campusano, the huge large quasar, big ring giant arc. They're all, you know, within my research team, but there are also other large scale structures in other teams, as I mentioned about the gamma ray bursts. So it is very easy to be skeptical about these structures, and I wouldn't push back against skepticism, because it could be that these are, you know, well, what are we really looking at? Especially with my method, that these magnesium 2 absorbers. So it can lead one to think, well, what are we really looking at? So, you know, the only thing we really can do when assessing observational data is use as many statistics as we can and to use different corroborative data. So I've mentioned that I've used both the quasars and magnesium 2 absorbers. So one's tracing the faint matter distribution, galaxies and galaxy clusters, and one's tracing the really bright stuff. So these are 2 different data sets. And what I do want to do is start to use more independent data, the DesiCluster data catalog, for example. Trying to think what are the questions. Yeah, so there's a lot more I can do with the big ring and the giant arc. And I really do want to get into the understanding what the magnesium 2 absorbers are telling us about the physical stuff that's there. So this is an ongoing field of research, the association of magnesium 2 absorbers and galaxies and galaxy clusters. What is it actually tracing? What is it actually telling us about the galaxy, the orientation, the morphology, all these things? So these are the big questions that I would love to answer, and I would love to give you the answers that I can. But right now, all I can do, you know, I'm towards the end of my PhD, all I can do right now is show that there's these statistical, you know, enhancements of mass in the magnesium 2. I can trace it with other types of data like the quasars, and just try to maybe, you know, present this as, you know, it's not, as I said before, it's not the cut-off kind of, you know, as it might be presented. The standard model's wrong. I'm not about to, you know, say Einstein was wrong all those years ago. But the interesting thing as well is large-scale structure studies and testing the homogeneity is a tiny fraction of trying to understand how good our standard model is. And there is plenty of tensions and things that you can find in other areas of cosmology that also might pose this kind of like challenge to the standard model. So it's not that I'm trying to, you know, push forward these cranky ideas and say everything's wrong, but actually what I'm trying to do is, you know, what you'll find is in cosmology, most people actually push back against my type of work because it's challenging the standard model. So it's actually arguably a little bit easier to be on the side of the standard model's great, and it really is, and the things that it has agreed with observationally and theoretically have shown that it's a brilliant model, but it needs still some pushing back to keep challenging, to keep, you know, testing its boundaries. So you've got to have both. You've got to have both sides of you know, the pushing against the standard model, the cosmology model. You've got to have those, and there are a lot saying this standard model is great, look at all it determines with its models, with its theories, with its simulations. And then you've also got to have, you know, the devil's advocate. You've got to say, well, what about this? How do you explain this? How do these large scale structures form? If they're not real, I mean, there's not really much I can say about that. All I can do is look at my data and try to interpret it the best I can with my very limited knowledge in this field. You know, there are many more people that are much more advanced in this field. So
will there be an archive version of this paper for us to evaluate at some point?
yes, there will. I think I shall have that out by the end of January. Thank you so much. And sorry for the ramble. Just have a question?
Yeah, Martin Radcliffe, Evans and Solon, excuse me. I was going to follow up on just to remind me, Ellen, this is for Alexia, apologies. It's such an intriguing topic, but can you give us some kind of reference to, I mean, we all know the cosmic web is there. You can look at that with Sloan data or whatever, and there's a very definite overall scale of that. And if you back out far enough away, it looks homogeneous. The scale of your both arc and ring, how does that compare in size to what we see the kind of general structure? I mean, I'm guessing what you're seeing is so much larger than any of the other filaments and voids and whatnot. Can you just kind of illustrate that a little more?
Thank you for your question. So yeah, we find lots of like structure, and especially in the SDSS, as you mentioned. So these will probably all be, I mean, you tend to find like tens to hundreds of megaparsec. So yeah, we're comfortable with megaparsec. I don't have to change to billion light years. So yeah, you know, we see these things on like tens to hundreds, and these are, you know, your structures, your large scale structures as well, and just not so large that it's, you know, exceeding this kind of like scale of homogeneity. So the big ring, its diameter is not actually you know, as big as the giant arc. I mean, if you looked at its circumference and using a statistical like MST type test, you do find its outside edge. So which is why I've quoted both the circumference and the diameter. But if you look at just the diameter, imagine it was just one clump of matter. It's only a little bit bigger than this scale of homogeneity. There's probably about 10 of these types of structures that are bigger than this kind of scale of homogeneity, but everything under that, if you keep getting on smaller and smaller scales, you keep finding things, you know, kind of like how when you zoom into a fractal, you'll keep seeing more and more structure, till the point where you're seeing, you know, structure in galaxies and structure in solar system. You can just keep going. Structure in people, structure in grass, just keep going. Yeah, thanks.
Carrie.
Hi, this is Carrie Hensley from the AAS, and my question is for Ananya. So I'm curious about this relationship you found between the time to peak brightness and the black hole mass, and I'm curious if that also applies to partial or repeating TDEs, or if it's only valid if it's a full TDE.
Am I audible? Am I audible now? Yeah, okay. So thanks for the question, great question. We did this for complete disruption of the stars. So this is not valid for partial, like the 30-day time scale is not valid for partial TDEs, and partial TDEs actually show a huge variation in time scale with respect to the beta parameter, which is the parameter that quantifies the distance of closest approach between the star and the black hole. But Julia and I are now working on extending this model to partials, and hopefully we'll have a paper which does that and also tests it against more numerical simulations to see if the model holds up. So,
great, thank you.
I have a question for Laura. So Zooniverse has come a long way since it started, and I'm curious by the way, this is Susanna Kohler, AAS. Sorry. And I was wondering what you kind of see as the ideal future for Zooniverse. How is it going to keep expanding? Are you hoping that more scientists will get involved and start their own projects? What's the capacity that you have on the administrative side for supporting that? And what does an ideal future look like for you?
It's a lovely question. Thank you. A future for Zooniverse, because we now have this robust infrastructure, machine learning integration, the ability to continue to scale in terms of number of projects. I mean, 10 million people around the world participating in science, that global collective impact is a really lovely sort of view of how we engage the public in science in a meaningful, authentic way that really leads to discovery. A huge part of all of that vision is the human-machine complementarity. There's so much of our infrastructure that's focused around how do we make sure we're not wasting people's time and stuff that models can do, and how do we keep knowing that there's that essential space for serendipitous discovery, the unusual, the weird. Machines are good at identifying what might be weird, but having human eyes in the loop to really pull out and see the things that we don't even, the unknown unknowns, that is very much part of the next, decade for Zooniverse. Mm-hmm. So it's an exciting space. And like I said before, very, very much welcoming and encouraging people to join us from the researcher community and from the public participants.
Do we have any further questions in the room, Carrie? Yes.
Hi, this is Carrie Hensley from the AAS, but I'm over here now. This question is for Timothy. So I think I heard you say that this galaxy was discovered pretty much serendipitously, and that this makes you expect that there are more galaxies like this out there. So were you able to discern anything about how common these galaxies are likely to be, or anything that would help drive a targeted search in the future?
Yeah, thanks for that great question. Because it's just one object at this point, I'm not really sure I can say confidently how many of these objects there would be. If you just assume that all the dwarf galaxies that we observe are kind of fair game for observing with JWST, you would expect that every few thousand JWST exposures, you would happen upon a dwarf galaxy. So the fact that we found this dwarf galaxy is consistent with the fact that we've got a lot of these dwarf galaxies, but it's hard to kind of extrapolate that from dwarf galaxies in general to this specific type of dwarf galaxy. But what you can do is, now that you have this idea of we should be looking for these more, is go to ground-based surveys that we now have deeper spectroscopic information, for example, from the DESI survey or the Gamma survey, where previously we haven't kind of really looked for this type of galaxy. And now if we kind of go back and look in more detail, like we're looking for this type of galaxy, they end up popping up more than I expected at least. And so that would be the way to go for looking for follow-up and more detailed information.
Great, thank you.
And did we answer all the questions that were online? I think we did. One more question from Leslie.
Leslie Sage, Nature. So this is for Timothy, and thank you for reminding me. What's the size scale of this dwarf galaxy? And do you have any spectroscopic data at all yet?
Yeah, that's a great question. So the size of this has a half-light radius of about half a kiloparsec. So it's a relatively normal size for a stellar mass. We do have spectra of this obtained with the Lowell Discovery Telescope to identify its redshift. And that spectra is consistent with a relatively old stellar population. It doesn't have a lot of emission lines you would expect from young stars ionizing the gas, but it's not deep enough to really give us a lot more information than that. So we're definitely interested in following that up with more deep spectroscopy to better understand its dynamics, for example, and more details about the stellar population.
Is it rotating? Or can you can't know yet?
I want to know. I don't.
Okay.
Any last questions? All right. Then with that, let's give our speakers a final round of applause here. Thank you so much to all of you. Thank you to your public information officers for helping prepare press releases and assist with everything. Thank you to our sponsor, USRA. And thank you to all of you for being here. Much appreciated. And with that, I think we can only go to, let's see, how do I get it onto the, you took care of it. Thank you. To the next slide, which is see you all in Madison this summer, June 9th through 13th for our summer meeting, AAS 244. Looking forward to it.